A star like the Sun is a massive ball of hot gas where extremely high temperatures and pressure exist in its core. Under these conditions, hydrogen nuclei collide and fuse together in a process called nuclear fusion. During this process, a small amount of mass is converted into a large amount of energy based on mass-energy equivalence. This energy is what makes stars shine and produce the light and heat that support life on Earth. In addition, nuclear reactions in stars also form heavier elements like carbon and oxygen, which are essential for life. In short, nuclear reactions in stars are fundamental processes that power the universe and make life possible.
What are the importance of nuclear reaction in stars? The recent literature shows that nuclear reaction in stars are central to three cognitive things: how stars shines, how elements are built, and how we reconstruct the chemical history of galaxies. First, Kobayashi's 2025 review links stellar nucleosynthesis directly to galactic chemical enrichment and modern survey data such as Gaia and James Webb Telescope. Second, recent abundance studies of fluorine and phosphorus showed how stellar reactions leave measurable fingerprints of the first stars and the present-day galaxy. And lastly, new experimental work on surrogate reaction, thin masses, and detector technology is reducing the uncertainty in neuron capture rates and our process abundance prediction. So, the importance is not just that stars shine, but the nuclear reaction in stars create the elements determine stellar lifetime and endpoints, and connecting laboratory nuclear physics to the origin of matter in the universe.
I'm Josiana Robert with student ID 2024441168. I will talk about methodology that we use. First, we use independent learning, which approach to gather information on nuclear reaction in stars. Besides, we also involve several systematic steps to ensure the accuracy and reliability of the information obtained. And we also use data collection, which relevant information was collected from various reliable sources, including educational websites, scholarly articles, and scientific publications. Online learning resources. We also use this from digital platform we utilize to enhance understanding of complex concepts, educational videos for visual explanation of nuclear fusion processes, academic website for additional explanations and examples. Last but not least, evaluation of sources. All sources were critically evaluated to ensure credibility and relevance. Consistent information across multiple reference, scientifically accurate and up-to-date content.
In our study of astrophysics, we have encountered three primary challenges that makes understanding stellar reactions is difficult. First is relating theory to reality. The first challenge is the distance. Because nuclear reactions happens far away in space, we cannot observe them in our daily lives. This makes the theory feel disconnected from our physical reality. Moving on to the next is the lack of prior knowledge. Processes like the proton-proton chain and also the CNO cycle are hard to distinguish because both involve the fusion of hydrogen into helium. To a new student, these complex cycles can easily be confused. And the last one is limited experimental evidence. We cannot recreate the center of a star in a normal lab. This makes it harder for students to fully visualize and trust the scientific theories being taught. To address these challenges, we have developed three proposed solutions to improve our understanding on this subject. First, we connect the science to life on Earth. We remind ourselves that the sun's energy supports all life, and that the carbon and oxygen in our own bodies were created by these nuclear reactions. This gives the topic a clear, real-world purpose. Next, we learn to trust indirect method. By using tools like spectroscopy to study sunlight, scientists can confirm what is happening inside a star. Understanding this method provides the evidence needed to validate the theory. Lastly, we need to have a strong basic physics knowledge. By reviewing fundamental topics like atomic structure, energy, and forces, we create a solid foundation. This makes advanced astrophysics much easier to process and understand.
Explanation of the concept. Nuclear fusion in stars. Nuclear fusion is the process where light nuclei combine to form heavier nuclei. This occurs at extremely high temperature and pressure inside stars. This releases a large amount of energy, explained by Einstein mass energy equivalence. Small amount of mass is converted into energy. For example, hydrogen nuclei fuse to form helium in stars. Main fusion mechanism. First, proton-proton chain occurs in smaller stars. Hydrogen form helium and energy. CNO cycle. This occurs in massive stars. Carbon, nitrogen, and oxygen act as catalysts. This converts hydrogen into helium. Importance of the concept. Explain the source of energy in stars. This produces light and heat from the sun that is essential for life on Earth. Formation of elements. Fusion creates heavier elements in stars. Supernova explosions produce elements heavier than iron. This explains the origin of elements on Earth. Understanding stellar evolution. This helps scientists studies the life cycle of stars and predicts star behavior based on mass and composition. Application in modern science. Contributes in fusion energy research. This is potential sources of clean and sustainable energy.
Next is about the factual details and examples related to nuclear reactions in star. Einstein mass energy equation explains how mass is converted into energy during fusion. In star, fusion happens mainly through the proton-proton chain and CNO cycle, which release large amount of energy. When hydrogen is depleted, stars form heavier elements such as carbon, oxygen, and iron. During a supernova explosion, heavier elements like gold and uranium are produced and spread into space. Moving on to the importance of nuclear fusion. Nuclear fusion produces the energy of stars, including the sun, which support life on Earth. Fusion also forms important elements such as carbon, oxygen, and iron. These elements are found in living things and planets. In addition, studying fusion helps scientists understand stellar evolution and support the development of clean fusion energy such as the ITER project.
First, the sunlight we receive every day is a direct result of nuclear fusion in the sun. This energy supports photosynthesis in plants, drives weather system, and regulates Earth's climate. Without it, life would not exist. Second, this energy is also used in modern technology. Solar panels convert sunlight into electricity, providing a clean and renewable energy source of homes and devices. Third, the study of nuclear reactions has contributed to medical advancement. For example, radioactive materials used in medical imaging are developed based on principles similar to nuclear reactions. Finally, all the elements essential for life such as carbon, oxygen, and iron were formed through nuclear reaction in stars. This means that everything around us, including our own bodies, originate from stars. In short, nuclear reactions in stars are not just theoretical concepts, they directly support life, influence technology, and form the basic building blocks of our existence.
Recent advances in nuclear astrophysics focus on better measurement techniques. Scientists can now study difficult reactions, especially for short-lived nuclei, using indirect methods like surrogate reaction. Improved detector technology increases precision by detecting small signals more clearly. In addition, precise mass measurements are improving prediction of how heavy elements form. However, despite this improvement, some important reactions, especially involving radioactive isotopes, are still very challenging to study. The main controversy is not whether nuclear reactions matter, but how to interpret incomplete data. Stellar cross-sections are hard to measure because they depend on tunneling, near threshold resonance, and interference, all of which are difficult to constrain experimentally. So different models can fit the same limited data while giving different rates. Second, controversy is how to read abundance fingerprints in old stars. Fluorine abundances in extremely poor CMP stars are being used to infer the nature of the first stars, but the interpretation still depends on which population third progenitor scenario is favored. That makes the stellar data to origin story powerful but not uniquely settled. A third controversy is about the endpoint of nucleosynthesis and the role of explosive events. Stellar reactions clearly build nuclei up to the iron in ordinary stellar burning, but heavier elements require neutron capture or explosive pathway, and an exact balance between these channels is still being refined. Overall, the trend is clearer in physics, but not complete certainty. The field is advancing through better experiments, better detectors, better surveys, and better reviews. But the remaining debates are about reaction rates, branching point, and how to translate observation into unique nucleosynthesis history.
Next, potential carriers related to modern physics. Astrophysics, the studies about stars, galaxies, and the universe. This applies concepts of nuclear fusion, and stellar evolution. This investigates how stars produce energy. Second, nuclear physics. The studies about atomic nuclei and nuclear reaction. Conducts research on fusion processes. Contributes to nuclear energy and radiation technology. Next, research scientists. They perform experiment and data analysis to develop theories related to modern physics, and they work in areas such as fusion energy and space science. Lastly, aerospace engineer. They design spacecraft, satellites, and space systems that applies physics knowledge in space exploration. They ensure radiation safety in missions.
There is a certain specific skills that we need to have for this chosen career path. First, an astrophysicist studies stars, galaxies, and nuclear fusion in the universe. This career requires strong knowledge in physics, mathematics, and data analysis. Next, a nuclear physicist focuses on radiation and nuclear reactions. They usually work in lab and research centers. Critical thinking and lab skills are important in this field. Another career is a research scientist. A research scientist conducts experiments, analyze scientific data, and develop new theories. Good research and communication skills are needed for this job. Lastly, a physics lecturer teaches physics concept and may also conduct academic research. This career requires deep thinking and good communication skills. To sum up, by studying nuclear reactions in stars, it can open opportunities in many professional careers.
Now, I would like to discuss about this part. First, modern physics is always evolving. New discoveries such as those from the James Webb Space Telescope continue to change our understanding of how stars form elements. This means we must keep updating our knowledge. Second, the tools used in this field are constantly improving. Scientists today use programming language like Python simulation and advanced data analysis. Therefore, continuous learning is necessary to stay relevant. Third, self-development is not only about technical knowledge, it also includes communication, teamwork, and research skills, which are important to working in scientific field. Finally, continuous learning allows individuals to adapt to new opportunities, such as developments in nuclear fusion reactor for future energy. In short, continuous self-development helps us stay competitive, improve our skill, and succeed in modern physics careers.
What are the common challenges in the careers related to astrophysics and nuclear in stars? A career in nuclear astrophysics, the study of nuclear reaction in stars, is rewarding but technically demanding. One major challenge is the science itself. Stellar reactions often happen at energy where cross-sections are extremely small. Many relevant nuclei are short-lived and direct laboratory measurement can be close to impossible. Another challenge is the training burden. You usually need a strong physics and mathematics, plus coding and data analysis, and often some experimental, computational, or observational skill, depending on your subfield. And lastly, career progression can also be slow and competitive. Academic path in astronomy often take 10 years period and may involve multiple relocations, while permanent positions are limited and competition is stiff. What are the strategies to overcome these common challenges? First, we need to build breadth early, then add a specialty. Strong base in physics, calculus, programming, statistics, and scientific computing will help, and then you can specialize in experiment, theory, or computation once you find the sub-area that fits you best. Next is get research experience as soon as possible. Working in lab, on simulation, or on data analysis might help you learn the field's tools, make the graduation application stronger, and show which part of the problem you enjoy. Investing in collaboration and communications, where nucleoastrophysics is too broad for one person to do alone. So networking, writing proposals, presenting clearly, and working across nuclear physics and astronomy groups are real career skills, not extras. Lastly, be strategic about choosing a niche. People who do well in this area often develop a recognizable strength, such as detector work, reaction theory, stellar modeling, spectroscopy, or computational nucleosynthesis, because that makes them valuable in collaborative projects and future jobs.